Today's lesson is on sampling distributions for sample means. The first thing we need to recall and remember is the difference between a statistic and a parameter. So pretty easy to remember. Parameter starts with a P, and it describes some kind of data point in population. So if I was to survey everyone in the freshman class and see their heights, that's a total population. And if I'm getting the average for that, that would be a parameter because we're dealing with the population. Now, if I were to take a sample of those students and get the mean, and maybe I pulled a sample of 20 kids and then another sample of 20 and another sample of 20, and I did that repeatedly over and over for 9th grade boys in high school or whatever you want to say, that's a sample, and what we get for mean for that is called a statistic. So sample starts with S, statistic starts with S, so it's pretty easy to remember. So you have to look at the differences of those. So there's an example about voting. Obviously we can't question every voter. It takes a lot of time and effort and money. So instead we do a sample. So we could do, like they do exit polls and things, maybe they do a random sample of 500 adults across North Carolina, and what they get is actually a statistic. All right, so that's the number obtained from a sample that is used to make a prediction about the whole population. That's usually what we do as researchers because it's less time-consuming and a little bit more manageable. Now, here's a couple of examples where you'd have to tell whether it's statistic or parameter. So a department store reports 84% of all customers who use the store's credit plan pay their bills on time. Well, if we're talking about a department store and we're talking about all of their customers, then that's what we have to focus on. This whole department store and all of their customers. So we're talking about all, this is going to be a population. So this is a parameter. So it comes from the population of the store's customers. A sample of 100 students at large university had a mean age of 22.1 years. Well, this one kind of gives it away. A sample, all right, and it's a sample of just 100 students at a large university. Well, obviously, if it's large, more than 100 students, so we know that this is a sample, which means that this is a statistic. It comes from the sample that we selected. It was generated to predict the mean age of all students at the university. The Department of Motor Vehicles reports that 22% of all vehicles registered in North Carolina are imports. So if we looking at Department of Motor Vehicles, it's talking about all vehicles registered in North Carolina. That keyword all is going to tell us that it is a population and a parameter. So it doesn't come from a sample, it's based on all the registered vehicles in North Carolina. So that's the first thing you have to recall and remember how to do. Now, let's think about if we pick 500 people and we get a statistic. So we just did one sample of 500 people and we get, say, the average. So the average is written as X bar, which means the average of the sample. But let's say we do this over and over and over again. 500, 500, 500, different random samples of the same population. We're going to have a lot of these X bars, and their little averages are going to be slightly different. Okay, they're not going to be exactly the same, and we expect that as statisticians. This is called sampling variability. Okay, so if we look at all those and we collect information from every possible sample of 500 that we can get, which would take some time, and we find the sample proportion from each sample, which means, let's say we find the mean from each sample, and we plot those on a graph, we would create what is called a sampling distribution. A sampling distribution is a plot of the statistics for every possible sample of a given size. So we're going to look at an example. So let's say we had measures of height of all boys in the 9th grade at our school. There's a lot of variability in the data. Obviously, some kids have grown tall, some haven't hit their growth spurt yet. And if we plotted each height of the boy, we'd end up with a curve that is approximately normal, with a center at 64.5. So we have 64.5, and a standard deviation of roughly 2. So that means this is 66.5, 68.5, 70.5, and then going the other way, a -1 would give us 62.5, 60.5, and 58.5. Okay, so our mean's right in the center. This is for one sampling, one population. Okay, so we know the standard deviation is roughly 2. Now, if we decide to take a sample of 40 boys from the 9th grade, and we do that repeatedly, over and over and over, and we plot, we're going to have some variability. But once we take all of those means from all the different samples that we do, 40 one day, 40 another day, 40 another day, whatever, many, many, many times, and then average those together, we're going to end up very close to 64.5. Because tall boys' heights end up negating the effects of the lower values, obviously. So it doesn't matter, even if we get a sample that's way high for their mean, you know, maybe we had a bunch of basketball players in there that we surveyed, and maybe the next day we had some younger kids or smaller kids, whatever. So you're going to have variability. But when we average all those together, we're going to be very close to 64.5, which is the population mean, which we should if we're doing good sampling. Now, when we take the average from the samples and we plot them, and then we pick that other sample and we find the mean and we plot it, and we pick it again and we do that again over and over and over, we'll create a curve that's similar to the one we made with all the individual data. But the curves will have a smaller standard deviation, okay? Smaller standard deviation, because when we use means, there's less variability. So we have a formula we have to use to find what that is. So let's look. This first one is a curve showing individual data, so that's like the population. That's like what we plotted up here. And this one shows what happens, and you notice that that curve is a little tighter together and a little bit more higher of a hump because the standard deviation from 0 at our mean to 1 standard deviation is going to be less because we used a bunch of samples of 40 boys. So let's talk about how that looks. So this is our formula. So sampling distribution of the means formula just means the mean of many sample means. This symbol here is the standard deviation. It's called sigma. This one is just what we get, just a normal standard deviation. But this has an X bar, right? It's like a little subscript. So this is saying the standard deviation of the means. Okay, so that's like if we have a big sample. If we just have this without the X bar, this is just a standard deviation of the population. And then N is our number of data points. And that would be, in our case, 40 for our boys. Okay, so if we did 50, it'd be 50. If we did a sample of 100, it'd be 100. 2 would be 2, so forth. All right, so let's look at how we would actually use this in an example, and then we'll go back to the boys. So the amount of time that it takes for a local fire department to respond to a local fire is strongly skewed to the right with a mean of 5.3, a standard deviation of 2.4. All right, so let's talk about that just in general. So the way that looks, we have here at our 0, this is 1, 2, 3, -1, -2, -3. So this would be our 5.3, and then standard deviation of 2.4 means from 0 to 1, that's a spread of 2.4, or variability of 2.4. So when we fill that out, we're going to have 7.7, and then add 2.4 again, 9, let's see, 10.1, and so forth. And here we'd have 12.5, and we could keep going if we needed more. And then we go back the other way as well. So when you take, just in your calculator, 5.3 minus the 2.4, and you do that repeatedly, and you'll have what these are. Okay? So when we think about that, that is one population. That is just like the whole population of what we have. So here's our mean. So it makes sense. I mean, we want somebody to report to a fire or a house. Average 5.3 minutes for them to get there. If it's rightly skewed, that means there's not going to be that many out here. At 12 minutes, our house will probably burn up pretty bad. But let's say we want to see what it would look like taking a sampling of 40 calls. So we do random sample, and we pull their data from their call logs, 40 random calls, see the response time. That's what we're going to look at. So we're doing a sampling of 40. This, what we just did, is just one sample. One population. Now, the next thing you need to know is that when we think about mu of X bar, or the average of the sample means, it should be close to 5.3 because we expect that to be true. If we do it over and over, we expect it to be like the population. So when you see something that's mu X bar is equal to mu, that is true. That's saying the average of the means, sample means, should be very close or similar to the average of the population. So that's the statement you have to know is true. Now let's look at how this works for our formula. So if we think about using this for 1, it wouldn't make sense to use a formula because we only are talking about one sample. So we take our standard deviation of 2.4, divide by the square root of 1, and we get 2.4. So that's the standard deviation population. That doesn't change anything. So it doesn't make sense to use it for 1. We're using it for many samples because remember, our variance is going to change. It's going to have less variability, which means our standard deviation is going to get smaller. So when we put in 2.4, this is our standard deviation from the population. That was what they told us from the fire department. This is our number of random samples. Okay, and then what we're finding is the standard deviation of the sample means. Okay, so we did that over and over and over and over. We're going to see how much variability we get. Now, we're just using 40, so it's going to shrink it. If we made this 100, shrink it even more. So let's look and see what this would be. 2.4 divided by the square root of 40, and we get, and I'm going to round here, 0.3795. Okay, so we get a very, very small number. We did have 2.4, and now it's 0.3, so it's less than a half. Okay, pretty big difference. So when we look at what that looks like, our mean still stays the same, 5.3. And then what we have for our variability now looks very different on our timeline or on our graph. So we would look, and I'm doing it on the same line here, we were going to look and see what we would have. So we would have 5.3 plus the 0.3795. So this would be, let's see here, calculator, 0.3795. This would be 5.6795. So let's look at the difference here. This 5.6795 is one standard deviation away, and this one, and it would fall like right around here on the one previously. So what's going to happen is that's going to make it really, really tight in our graph, and it's going to make this peak higher because the variability is smaller. Okay, so back to our boys, what that means, if we look at them, we would think about how do we find the standard deviation for them. So if we are looking for, say, the 40 boys, let's go ahead and use our standard deviation. Our standard deviation was 2. So we're going to do standard deviation x bar. Population standard deviation is 2. Square root of 40. And let's see what we end up there. 2 divided by the second square root of 40. We get 0.3162. Okay. So what that means is right here, when we're doing it for a sample, this is still 64.5 as our mean. But here would be 64.9, and again, I shouldn't be rounding, but to show you, and 65.3, and this is 65.6, this would be 64.1, and you get my drift. So when we look at the difference, notice how the standard deviation has gotten much smaller, because there's less variability or less change between standard deviations. All right, so let's look at one for a kitten after we look at our conditions. So to be able to use sample means of sampling distributions, we have to meet some conditions. Our samples have to be random. We have to make sure there's no bias. They actually fit the population we're looking for, and they're randomized. We're going to assume independence, meaning that one doesn't affect the other. So like the height of a 9th grade boy would not be affected by the height of another 9th grade boy. So independent. Same thing with fire trucks. One call does not affect the other calls. There's a 10% condition rule, which means that our sample size has to be under 10% of the population. So if we have just a sample or a population of 100, then we'd have a very small sample size to be under 10%. But if we're talking about a fire truck or a firehouse, they probably get hundreds and thousands of calls a year. So picking 40 is definitely under the 10% rule. Your sample must be big enough. We talk about picking 30 all the time, and that's kind of a general rule of thumb. But You only really need 30 for sure or more is if your data is skewed. So if it's non-normal distributed or skewed left or right, you definitely need 30 or more. If it's normally distributed, you can have any size. You can have 2, 5, 7, whatever. But those are your conditions. Now, let's look at a little kitten and talk about how we use our calculator. So the weight of a kitten are normally distributed. That's important to know, so we can have any sample size that we want, and has a mean of 3.6 and a standard deviation of 0.4. We're going to find the probability that a kitten weighs more than 2.9 pounds. So when we think about what we're doing here, we have a normal CDF in our calculator. We are looking for something more than 2.9. So this is our minimum to our max. This is our mean, and this is our standard deviation. And we put in our calculator, and we get 0.9599, or 95.9%. Now, this is not a z-score. This is actually the area under the curve. So if we wanted the z-score, we would have to take the 2.9 minus our mean of 3.6 and divide by our standard deviation of 0.4, and we get a z-score of negative 1.75. Okay, so make sure you know the difference of what's going on. Now, that's just one. That's just one kitten. In general, we just pull one. Okay, now, what if we look at a sample size that's larger than 1? So sampling of the means. So still has the same mean of our kittens, still standard deviation, but now we're looking for a litter of 6 that has a mean weight of more than 2.9 pounds. So the first thing we have to do, because we're looking at a group, is we have to find the sampling distribution standard deviation. It's obviously going to be smaller because when we pull a whole bunch of data in our samples of 6 kittens and 6 kittens and 6 kittens, we're going to get a smaller standard deviation. So we're going to find out what that is with our formula. So we use our original one of 0.4, and we divide by the square root of our sample size, which is 6 in this case, and then we get 0.1633. Okay? So if we were using our calculator, we put it in, same way, we're still looking for something bigger than, more than 2.9 pounds, so minimum, maximum, this is our mean, and this is our new standard deviation for the mean. So we get 99%, okay? Now again, if we wanted to find z-score, our z-score is, remember, our raw data, so if we're looking for something that's 2.9, we would have to look at, and then this time, same as we did up here, the difference is our standard deviation that we divide by is now different. So we have 2.9 minus 3.6, this time divided by 0.1633. So let's see what that would be. 2.9, using my little calculator, so helpful. I would get a negative 4.286. That would be my z-score. Okay, and your table doesn't go to that. So we're going to talk about how to use Desmos and put it in Desmos. So let's look at Desmos here. So if we went ahead and put it in, we do it as normal distribution, and we put in our mean and then our standard distribution. This is for our population. So this was when we were just doing one cat probability of having one kitten that's larger than 2.9. We put it in the CDF, we have to click and then put 2.9, and we see what's shaded there is that. Now, if we want to then see about the 6 kittens, we would have to change the standard deviation to what we calculated. So 0.1633, the average stayed the same, CDF 2.9 to maximum, and we get 0.99. Now let me show you what that looks like in our graph. So when I turn that on to plot it, notice that it's more compact, it's more close together, which tells you there's less variability because our sample size was 6. Now if we went up to 12 kittens and so forth and over, that would change that standard deviation, and it would get tighter and tighter and tighter all the way up and get a little more peaked and a little tighter. And that's actually called keratosis, which there's a little information about that on Canvas. If you see that word, so you know what it is. Okay? Now, we're going to look at what that looks like in a demonstration. So I'm going to show you a little demonstration here. I'm going to clear these. So this is a normal distribution, and we have a mean of 16. Our standard deviation is 5. And if I were to take a sample of, let's say, 5, I do a sampling of 5, random sample 5, over and over and over, and I get the average every time, I'm going to then plot it. So it's going to actually show in this second chart, me pulling it, so I'm going to animate it. It's going to pull 5 examples, and then it takes the average. And it does that repeatedly, okay? Now, this time it's pulling 25, and it's going to plot them at the bottom. And we're doing the mean. So one group is a sample of 5, the other group is a sample of 25, okay? So if I continue to do that, I'm going to do 5 more, and watch what is happening to the mean over here. So on the first one where I just had a sample size of 5, my mean is at 16.85. It's pretty close to the original, but here my mean is a little bit lower. And that can happen because we're doing random sampling. We could get a sample that has a little bit, different variability in it. That's why we have all that differences, and that's why we continue to do more sampling. So let's do some more. Let's say we add 5 more, and 5 more, and more. Maybe we add 10,000. Look at what's happening. Our median from our original is 16. Our median for a sample of 5 is 16, and it's 16.01 for 25. But look at our standard deviation. We started with 5, and now with our sample size of 5, it went down to 2.2. But with our sample size of 25, it went down to 1.03. So the larger the sample size, the less variability. The smaller the spread is, or the standard deviation is, for our sample distribution of our means. So if I had 100,000 and I continue to add, you'll see that it gets to a point where it kind of just levels out, okay? But I want you to notice our standard deviation and our means. Means are all identical now. Our standard deviations got smaller as we added more samples to our size of our random sample. All right, so we are going to look at what that leads us to. So seeing that that happens leads to a theorem called central limit theorem, which can be abbreviated as CLT. And this is a calculus, advanced AP concept. It's just saying that when you're given a mean that's finite, which means it has bounds and limits, and you're given a non-zero variance that is clear, like standard deviation of 2 or 0.5 or whatever, that if we take these samples over and over and over, sample sizes, and the larger we get with our sample size, the standard deviation will decrease. That's all it's saying, just what we just showed in the demonstration. So that's the central limit theorem, okay? And it doesn't matter how it starts out looking. It can look like a crazy, histogram like that with little bars all crazy. And eventually, when we take all the samples, it will be a normal distribution. Terrible pictures there. All right, so some takeaways, things that you have to know. Sampling distributions are centered around means or proportions. When our situation calls for a sampling mean, you should know the following. The mean of the sample distribution is equal to the mean of the population. That's just where I said mu of x bar is equal to mu, that's true. That's what that means. The standard deviation of a sampling distribution will be smaller than that of a population. So we just seen that in our demonstration, that our standard deviation gets smaller and smaller with our sample sizes increasing compared to just one population or parameter. The sample size increases, so if we go from 10 to 40 to 100, the standard deviation will decrease, and the distribution will have less variability. It's that tighter that we saw in Desmos, so it's pretty clear. Now, the standard deviation of the sample distribution, which is basically the variance, is equal to the standard deviation of the population divided by the sample size. And that should say divided by the square root of the sample size. So that was our formula that we talked about. Hopefully this helps.